Chemical reactions are happening around us all the time. When you toast bread in the morning, a chemical reaction called the Maillard reaction gives it a delicious flavor and brown color. Another example is when you mix baking soda and vinegar to create a fizzy explosion, perfect for a homemade volcano experiment. These everyday occurrences show how chemical reactions are not just something you learn about in a laboratory, they are a part of our daily lives. Chemical reactions are the processes that change substances into different ones. They involve the breaking and making of bonds between atoms. For instance, when you light a match, the chemicals in the match head react with oxygen in the air to produce a flame. This simple act is a chemical reaction that releases energy in the form of light and heat, allowing you to start a fire. Not only do chemical reactions create new substances, but they are also responsible for the energy exchanges that power our world. From the combustion of fuel that drives cars to the photosynthesis that allows plants to grow, chemical reactions are essential for life as we know it. Recognizing these reactions in everyday context helps us appreciate the hidden magic of chemistry. By understanding chemical reactions, we can manipulate them to our benefit. For example, in cooking, knowing how yeast ferments dough can help us make perfect bread. In medicine, understanding chemical reactions allows us to develop drugs that can cure diseases. Thus, recognizing and harnessing chemical reactions is crucial for innovation and progress in many fields. A chemical reaction is a process where one or more substances known as reactants transform into different substances called products. Common examples include rusting iron, where iron reacts with oxygen to form rust, and the digestion of food, where complex molecules are broken down into simpler ones. These transformations are crucial as they often result in the formation of substances with new properties. Chemical reactions can be categorized into various types. A combination reaction is when two or more substances combine to form a single product, such as when hydrogen and oxygen combine to form water. Decomposition reactions involve a single substance breaking down into two or more simpler substances, like when an electric current passes through water, splitting it into hydrogen and oxygen gases. Displacement reactions occur when one element replaces another in a compound, as seen when iron is placed in a copper sulfate solution, resulting in the displacement of copper. Double displacement reactions involve the exchange of ions between two compounds to form new compounds, such as when silver nitrate reacts with sodium chloride to produce silver chloride and sodium nitrate. Chemical reactions are not limited to these categories. Redox reactions, which involve the transfer of electrons between substances, are prevalent in processes such as combustion and photosynthesis. Understanding the different types of chemical reactions helps us predict the outcomes of chemical interactions and harness them effectively in various applications. Identifying a chemical reaction can be exciting. One of the most common signs is a change in color. For example, when you add iodine to a starch solution, it turns dark blue, indicating a chemical reaction. Another sign is the release or absorption of heat. When you touch a hand warmer, it feels warm because a chemical reaction inside releases heat, an example of an exothermic reaction. Gas release is another indicator. When you mix baking soda and vinegar, the fizz you see is carbon dioxide gas being released. Similarly, when effervescent tablets dissolve in water, they release gas, demonstrating a chemical reaction. The formation of a precipitate, a solid that forms from a solution, is also a sign. Mixing solutions of lead nitrate and potassium iodide forms a yellow precipitate of lead iodide. Chemical reactions can be represented using chemical equations. These equations use symbols and formulas to show the reactants and products involved. For example, the reaction of hydrogen and oxygen to form water is represented as 2H2 plus O2 yields 2H2O. Each symbol in the equation represents an element, and the numbers indicate the quantity of atoms involved. Balancing chemical equations is crucial because it follows the law of conservation of mass, which states that mass is neither created nor destroyed in a chemical reaction. This means the number of atoms of each element must be the same on both sides of the equation. Balancing helps us understand the proportions in which substances react and ensures that our calculations in chemistry are accurate. Chemical reactions are classified based on how reactants transform into products. Combination reactions are simple and involve the joining of two or more substances to form one, for instance, when nitrogen and hydrogen form ammonia. Decomposition reactions, on the other hand, involve a single compound breaking down into simpler substances, like the electrolysis of water into hydrogen and oxygen. Displacement reactions involve a more reactive element displacing a less reactive one in a compound. For example, when zinc is added to hydrochloric acid, it displaces hydrogen, forming zinc chloride and releasing hydrogen gas. Double displacement reactions occur when ions from two compounds exchange places, such as when barium chloride reacts with sulfuric acid to form barium sulfate and hydrochloric acid. Exothermic reactions release heat, making the surroundings warmer. Combustion, like burning wood, is a common exothermic reaction. Conversely, endothermic reactions absorb heat, resulting in a temperature drop. An example is the reaction between barium hydroxide and ammonium thiocyanate, which absorbs heat and feels cold. Corrosion and rancidity are undesirable chemical reactions. Corrosion, like rusting, occurs when metals react with oxygen and moisture, weakening structures. Preventing corrosion involves using protective coatings or galvanizing metals. Rancidity is when fats and oils spoil, often due to oxidation. Storing food in airtight containers or adding antioxidants can help prevent rancidity. Understanding chemical reactions allows us to mitigate these issues, enhancing the longevity of materials and food products.